Are you ready, team? We're going to get in some juicy stuff today. We're going to be we've been talking about atoms and then bonds and bonds and bonds and bonds and bonds. Now we're going to put all those pieces together because obviously most molecules have more than one bond, right? Diatomic molecules have one, but it's things as simple as carbon dioxide and water have two bonds. You know, water like this, CO2 like that. You get up to things with 4, 5, 6, 7 bonds, you start to get to biochemical molecules. They could have hundreds or thousands of bonds. Right? We put that's called a molecule. So we have to put that whole thing together. We want to really get, our ultimate goal is to really look at how this particular species, this molecule, especially in organic chemistry or biochemistry, how does it react? If we look at this chemical as a whole, is there, it may have a lot of stuff, fluff and stuff, but maybe there's one region on there that an enzyme can come in, right? Or some drug can attach to it. So that we call that an active site, right? But the whole three-dimensional shape of that molecule determines that one little spot. It might be this huge molecule, and this one little tiny spot over here has this very specific three-dimensional shape, kind of like a lock, like on your front door of your car. And only one key can fit in that particular shape. And the whole molecule folds and bends and has all these angles so that that one little portion has that specific shape that another drug or medicine can connect to and work, or a neurotransmitter or something like that. It's fascinating. Think of it like a lock and a key. So only one specific shape will fit in that. Well, how do we determine that shape? Oh, that's what we're going to do today. The VSEPR theory. This is a fairly simplistic theory that works mostly just for like the, row 3, maybe row 4 elements, things like that. Kind of the predictions and stuff kind of don't work as well as you get further down the periodic table, but it gives us a general look at the shapes of molecules, which can give us a general look at how it reacts and things. Obviously, computer simulations and computer models using Schrodinger's equations and quantum mechanics works a lot better, but we don't always have that at our disposal. So this is more what they call like a back of a napkin. You're at lunch, you can just take a napkin, flip it over, maybe get some mustard stains on one side, and you can just scribble through, and within a minute or less, you can go, yeah, this is pretty close probably to what the shape is, and it's amazing how well it matches the experimental values. So we'll go through and describe what VSEPR is, what it means, it's an acronym, how it works, and just how simple it is. I'll probably have to break this into 2 videos because it takes a while. So we'll do molecules that follow the traditional octet rules. And then in the second one, we'll look at expanded octets. Get some really cool shapes with expanded octets. Gets a little weirder though, but this is the same theory behind it. And then we'll look at complex molecules. I'll just keep it with simple ones at this point where we have one central atom, and then we'll get to expanded octets and complex molecules in the second video. So in general, when I talk about what do I mean by shape, molecular shape? Okay, we're looking at the three-dimensional shape, how the atoms, typically we focus on a central atom and how the other atoms are arranged around it. And if we have a complex molecule, we have lots of central atoms with ways those atoms are bound to it. So for example, let's say we have something like this, and planar means flat like this, but if it breaks, 2-dimensional, but a lot of them break up into 3 dimensions, which is kind of hard to do on a 2-dimensional surface. So I'm going to have to show you things called dash wedge structures or VSEPR structures. But let's say we got some central atom in green there, whatever it is. Let's say it's bonded to 2 atoms in pink that are the same, and another atom over here that's blue. However it is, doesn't matter. Well, we know we've got the bond length, so we got this bond length, that bond length, that bond length. If these are the same, then D2 and D3 would be the same. But bond length is just the distance between the nuclei. We already know how to do that. Just take the covalent radii. Now, in reality, this is kind of a ball stick model. In reality, these are touching. This green one's huge, and the pink one's touching it, so they're actually overlapping a little bit. But this allows us to see things a little bit better. You'll see that with different computer-generated images. Some of them will show you a ball stick model. Some of them show you the orbital overlap. But just take the covalent radii and add them together. So bond length's easy. VSEPR is not going to give us bond length, but it'll tell us what the atoms there are. But what we're mostly after here with VSEPR is the bond angles, this little alpha symbol. So we've got this bond angle here, this bond angle here, and this bond angle here. That's what VSEPR is going to allow us to kind of predict. It's fairly accurate for, the n equals 1, 2, 3 shells. When you get further down, it's not as accurate, but it tells you if it's linear or bent type of thing. We can get a rough guess on the actual angle. But this is all based on the Lewis structure. The Lewis structure is two-dimensional, right? Just shows you the atomic connections and whether you got double or triple bonds and lone pairs, those kinds of things. The VSEPR, think of it as the Lewis structure busting into the 3 dimensions if necessary. So let's take a look what VSEPR stands for and get into it. I got my trusty little model set. I highly recommend, if you're ever planning on taking organic chemistry, invest in a really good molecular model set. The one I have is called a MollyMod set. And we're going to do a whole lab on that so you get used to it. Doing all the cool little shapes. Whee! It gets kind of fun, and then you lose them and the atoms roll around on your floor. Let's get to it. All right, this acronym works really good. I have one tiny issue with it. We're going to fix that one, but that's just for my class. So let's take a look. Just understanding, we've talked about this before, when 2 atoms come together, they got their nuclei, n equals 1, n equals 2, n equals 3. So they got the inner or core shell electrons and then the outer ones, right? And when those atoms come together, they overlap, and they can share electrons in a covalent bond, transfer electrons for an ionic bond. We'll find out it's not so black and white. It's all kind of partial ionic and partial covalent. Nothing's perfect, is it? And then, once they settle into their bond length and nuclei, you can get the covalent radii and you can calculate the bond length. So we'll just keep a simple bond here between atom number 1 and atom number 2. So VSEPR is an acronym that kind of talks about how these particular atoms are going to come together. But let's say this actually connected with several atoms. Right? Let's say we got another one here. Say we got an atom here. Let's call that atom number 3. And let's say we got another one here. Love my beautiful circle there. Atom number 4. Those, if you're an engineer and I draw an imperfect circle, it bugs you. It's not symmetric. So obviously when these overlap, here, here, and here, we've got the bond lengths, we got the nuclei. It's the valence shells that overlap. Everybody agree? Okay, you probably know this already. So this stands for valence shell. Right? That's where the V and S come from. And what's overlapping? It's not the nuclei, it's not the protons and neutrons. They're not involved in these bonds. It's the electrons. Told you this was simple. Valence shell electrons. That's what overlaps, right? Now, once the bonds are formed and you have the electron, you got the bonding groups, right? Either single, double, or triple bonds, and you got non-bonding groups, which are the lone pairs, and within the bonding groups, a single bond is 1 pair, double bond is 2 pairs, triple bond is 3 pairs. That's where the P comes from. Now, if I had a negatively charged group here, right? So let's say this is negative, and this is negative. Those regions of electron density, whether it's a single bond with those 2 electrons, a double bond with 4 electrons, a triple bond with 6 electrons, or even a lone pair, those regions of space contain negative charge. Do you think that negative region of space and that negative region of space are going to be attracted to each other? Wait. Like charges repel. So this is repulsion. So what I'll do in the next board is write out a sentence on what the basics of this theory is. It's fairly straightforward. Regions of negative electron density repel each other. So that's a repulsion energy. So they're going to get as far away as they possibly can from each other to minimize the electron-electron repulsions, or go to the lowest energy 3-dimensional configuration. It's just a natural thing. Nature loves the lowest energy state, which would be the electron regions are as far away as possible. Now, I have an issue with the P here. I'm going to put a star. Would you agree that a triple bond is not 1 pair? It's 3 pairs, and so students get confused. You can't think in terms of pairs. You have to think in terms of regions of electron density. So a triple bond and a double bond and a single bond are all 1 region of space, right? So if that was a triple bond, it would still be the same region of space, just more electrons crammed in there. But a triple bond, double bond, and a single bond are all treated as 1 region of space, or 1 group. So I like to think of this as group. So think about it. So I like to say VSEPR, right? VSEPR is better. If you think of it in terms of pairs, you'll actually get answers incorrectly. Think of it in terms of electron regions or groups. All of them treated the same. Let me summarize that on the next board. And understanding that they're just going to maximize their distance to minimize the repulsion energy, you can figure out a lot of shapes. To summarize what I was just saying, this kind of puts VSEPR in a nutshell right here. Right? We're focused on central atoms, right? The key here is central atoms. So if we have a complex molecule with 2 or more central atoms, we can only apply VSEPR to each individual central atom as a whole. You can't do the molecule as a whole unless it's simple. Simple molecule has 1 central atom, so technically you could get the molecular shape or molecular geometry. I hear both people say molecular shape, molecular geometry of the molecule as a whole if it has only 1 central atom. Right? Pretty simple. But once you get a complex molecule, it gets a little trickier. You got to do each one in turn. So regions, obviously, of electron density will repel each other, right, about that central atom. So here's a central atom. You could have a single bond here, double bond here, lone pair here. They're all going to repel each other. Those electron groups, don't think of them in terms of pairs. Think VSEPR, not VSEPR. Those electron groups, we'll define those on the next board, will orient as far apart as possible. Electrostatic repulsion, baby. Get as far apart as possible in 3-dimensional space, right? The resulting structure, by maximizing their distance, minimizes those repulsion energies, which gives you the lowest energy structure. That's the one nature will always go to. Nature always goes to the lowest energy state. Woohoo! Unless we blast it with some energy and put it in an unnatural state. Let's talk about let's redefine central atoms and electron groups. Here's our crisp, clear definitions. Remember, don't think in terms of electron pairs repulsion, think in terms of electron group repulsion. They're all equivalent. So here's what we're going to define as electron groups. Any region of electron density. Okay, so that counts as a single bond, double bond, triple bond, 1 pair, 2 pair, 3 pair, but they all count as one group, and these are the bonding groups, single bond, double bond, triple bond. Same region of space, just different numbers of electrons trapped in there, but they count as one group in the VSEPR theory. A lone pair, right? You got the non-bonding group, or a single electron, a free radical electron. That still is a region of electric charge, negative electron charge. So those are your non-bonding groups. There you go. So we only have 5 groups. That's it. So you look at the Lewis structure, look at a central atom, which is and this only applies to central atoms, which is an atom bonded to at least 2 other atoms, right? It's in between them. And you just look at the Lewis structure and count how many electron groups are around there. And boom! So we're going to go through a lot of possibilities because we're going to be getting into expanded octets in the next video. Yarg! Here we go! 2 types of shapes or geometries that we are going to be looking at. We're going to look at electron group geometry and molecular geometry. Now, I put a star next to molecular geometry because that's what we're ultimately after. So when somebody mentions, hey, what's the shape of that molecule or what's the geometry of that molecule, this is what they're talking about, molecular geometry. Electron group geometry, all that is the arrangement of all the electron groups around a central atom. Single bonds, double bonds, triple bonds, lone pairs, free radical electrons. How are they arranged in 3 dimensions? Boom. Doesn't matter if it's a bonding group or a non-bonding group. That's irrelevant. How are those electron pockets, regions, repulsing and orienting in 3-dimensional space? That's called an electron group geometry. And we only have a handful of types, 5, I think. You can either have 2, 3, 4, 5, or 6 electron groups, right? So only 6 possibilities. 2, 3, 4, 5, 6. That's not 6, that's 5. Molecular geometry is the arrangement of atoms about a central atom. That's what we're really interested in. So in a molecular geometry, if something has a lone pair or a free radical electron, yes, it does influence where the electron groups are, but we don't see that. That's not an atom. So we're only looking at the resulting atoms around that. So sometimes those are the same. If all of the electron groups are bonding groups, every electron group has an atom on the other side. Then these would be the same. But if you have an electron group that doesn't have an atom on the other side, a lone pair or a free radical electron, then the molecular geometry will be different than the electron group geometry. So let's go through the 5 different electron group geometries, and we'll show you all the different combinations of resulting molecular geometries or shapes based on whether we shove an atom on the other side of that electron group or not. We'll start easy. We'll start with the skateboards to get to the tricycle, then the bicycle, then the motorcycle, then the Lamborghini, and then the jet airplane. All right, let's start with 2 electron groups. Let's say we have A, we'll just call A some central atom. And let's say it only has 2 electron groups. So that could be a triple bond and a single bond, 2 double bonds, right? Whatever it is. And let's just call those blue regions of electron density, 2 groups. So we have 2 electron groups. Well, they're going to, so if my head's the central atom, and this fist is an electron group, and this fist is an electron group, they're not going to be at 90-degree angles because they're repulsing. They're going to go, and try to get on opposite sides of each other, right? Like standing in a line. You got one person in front and one person behind at a 6-foot distance, all right? So that creates a 180-degree bond angle. That's the natural flow of that. So that creates a straight line, so we call that a linear electron group geometry. Now, if we stuck an atom on either side, that would be a linear molecular geometry as well, but we'll do that later. I'm just looking at electron group geometries. So let me draw up, try to do it, try to jump ahead of me, try to do 3 electron groups. So feel if you're the central atom and you had 3 electron groups, like 3 arms, how would they, and they're repulsing, where would they go to maximize their distance and minimize their repulsion energies? Think about it. Think about it in terms of a circle and what those angles would be. Did you figure out the 3? So if you have 3 electron groups, right? So let's say we have some central atom and you have 3 regions of electron density, they're going to orient as far apart as possible, and form looks, kind of like some boat propeller or something like that. But you see the angle here? That's a third of the circle. So that bond angle is going to be 360 divided by 3, right? 120-degree bond angles, and it's flat. Do you see how that's flat? So we call that planar. So it's trigonal planar. It's a flat triangle. Whee! Right? There you go. See if you can do 4 electron groups for me. 4 got tricky. Were you tempted to do a square? Right? You put it in there, and then if you do a square, if you keep it flat, you get a square that would be flat or 2-dimensional, but that would give you 90-degree bond angles. No. Once you get to 4 electron groups, boop! It pops into 4 dimensions. So if we have a central atom, imagine you have 1 up, you have 3 coming down, forming kind of a pyramid, a 4-sided pyramid, and then you got 1 coming kind of at your face, you got 1 kind of coming at my face, and you got 1 kind of coming down the line. And you can orient this. I've seen different textbooks orient them different ways. I have a particular way I like it. If you're a Dungeons and Dragon person, this is my old 4-sided die from like 35 years ago. My God, more than 35 years ago. I got my D&D first dice set, and I still have it. It's all worn away from the nervousness. Oh, come on, roll 4. Anyway, I just had to throw that in there. So once we get 4, it busts into 3 dimensions. So instead of 90-degree angles in 2 dimensions, you get what's called a tetrahedron. This shape's called a tetrahedron, or it's tetrahedral in shape, and it has 109.5-degree bond angles. That's further away than 90, so nature automatically goes to 3 dimensions. Now, how do you draw a 3-dimensional structure on a 2-dimensional surface like a board or your piece of paper? We need a dash wedge structure, which I call a VSEPR structure. So if I say, hey, draw a VSEPR structure, I mean the dash wedge structure. So you just draw your central atom, and this would represent, right, 1 coming straight up, right? So that one's coming straight up. This one's coming straight out. Those are in the same plane, right? These means they're in the same plane. And then you'd have this one coming at you, right? So if these are in the same plane, this one's coming at your face, and this one's coming away from your face. So this one's coming, this solid wedge is coming out of the plane towards your face, and the dash wedge is moving out of the plane away from your face, right? So these model sets give you the kind of what looks like the dash wedge structure. And then we may or may not put atoms on the other side. Woo! Let's get to 5 and then 6. Did you get the 5 electron groups? Ooh, it starts getting weird. This requires an expanded octet. We'll do on the next one. So with 5 electron groups, you get 3 dimensions. So you get an axis. So you got the central atom with 1 straight up and 1 straight down. And then in kind of the equator, you get a triangle. You see those 3? See the 120-degree bond angles? And you flip it up. Do you see the 90-degree bond angles? So we have some asymmetry to this, all right? So when you have the 1 straight up and the 1 straight down, you have what are called axial positions, kind of like going from the north to south pole on the planet. And then when the planet spins around, you have the equator, right? And the equator, you have 3 that are in the same plane. So you get this one here, one here, one here. But this one's actually going out of the plane. This one's going towards you out of the plane. So you get the 90-degree angles between the axial and equatorial positions, right? 90 degrees here. And then within the equatorial positions, you get 1/3 of a circle. So it's like trigonal planar in the it's like trigonal planar with one up, one down. It's like a top. You could spin it like a top. So 90 degrees between axial and equatorial, 120 between equatorial. And if you draw that as a dash wedge structure, you just draw the central atom with one straight up, one straight down. Those are in the same plane. And then I rotate it so that I have that one also in the same plane, right? So those 3 electron groups are in the same plane, so we use lines. And then this one here is coming out at your face, and this one here is coming away from your face. See that? So you use an open wedge there and a dash wedge there. Oh, this creates some interesting structures later. One last thing real quick. When you're looking at the shape of something with 5 electron groups, it's a little trickier. It's called Trigonal Bipyramid. What does that mean? That's the shape. So would you agree that if we looked at it this way, you've got from the center kind of a flat triangle, and so it's like a trigonal pyramid on the top, but then a trigonal pyramid on the bottom. So if you take a triangular base pyramid and two of them and glue them at the bases, that is what you get. So trigonal bipyramid, 2 triangle pyramids glued at the bases. Oh, with the 120-degree bond angles and the 90-degree bond angles. All right, now we can do 6 electron groups. How'd you do on your 6? Hey, if you got a model set, you could do this at home, right? So when you get to 6, it's a lot like 5. So 5 had the triangle and the equatorial and one up, one down. Well, 6 electron groups, the same thing. You've got the one up, one down, but you got a square instead of a triangle in the, although it's perfectly symmetric, so you don't really have axial and equatorial positions. But I like to think of it as a, one up, one down with a square in the middle, right? Can you see that square is flat? See that? And then you got the one up, one down. But every single angle is 90 degrees. 90 degrees. Everywhere you look, that's perfectly symmetric. So all bond angles are 90 degrees everywhere. You don't have to write it all. You just have to say 90 degrees. That gives you an octahedral shape. Or in Dungeons & Dragons, the 8-sided dice. That's why it's octahedral. It has 8 sides to it. Yay, I love this one. And if you do the dash wedge structure, obviously you got the top and the bottom in the same plane, right? And then you orient it. I mean, there's different ways. The way I have it oriented, you've got these 2 coming out at you. So those are the solid wedges. And then these 2 behind are coming away from you. So those are the dashed wedges. Boom! Everything's 90 degrees. Yay! You know what? I think I'll stop it here. I was going to do some molecular shapes, but I think I'll just leave it on this first video as electron group geometries. And then the next one we'll do molecular geometries. We may even need to break that into 2 videos. We'll see.